I'd like to welcome everybody to the last session for today's 3DV. This is an invited talk session, and our keynote speaker today is Professor Lingjie Liu. Professor Liu received her PhD from the University of Hong Kong in 2019, and she then spent 2 years as a postdoctoral fellow at the Max Planck Institute for Informatics. She is currently the Aravind Joshi Assistant Professor in the Department of Computer and Information Science at the University of Pennsylvania, US. She's also a member of GRASP Lab. Professor Liu has published impactful research work in the area of neural scene representation, human modeling and capture, and 3D reconstruction. Her title today will be Generalized 3D Reconstruction, and I'd like to welcome her with a round of applause. Thanks for being with us.
Thanks for the kind introduction. I'm honored to be here to present our recent work on 3D reconstruction. I'm Lingjie Liu from UPenn. With the development of video models and multi-view models, now people may ask, like, do we really need 3D? I think the answer is yes. We live in a world that is 3D. So we digitize our world in 3D. In this virtual world, we can visualize from arbitrary views. We can also use to control and interact with our virtual world. As shown here, you can edit and move the object in the virtual world. Also, for the future generative AI, for the future AI, actually, it should be towards 3D aware. So the AI systems can help humans in 3D, like interacting with and helping people in the 3D sense. So my research goal is to reconstruct these complex things in the real world. As shown here, like the robot interacting with this object in factory, and people dancing, and we driving the cars on the street. Like, we want to reconstruct the geometry and appearance models from these videos. And we also, because we live in a dynamic world, so we also need to capture the motion and the deformation of the dynamic things. Hopefully, this can be done like using the videos or image that are captured by a single RGB camera. If we go back to 10 years ago, there are a line of amazing works in traditional image-based reconstruction, like this Build Rome a Day or Core Map. So they can reconstruct the 3D thing using the images on the website, and then to have this dense point cloud. Okay, actually this is amazing. We first time can reconstruct this 3D things from the 2D images. And here we show without using Core Map on 100 input images of this car. Although there is a great progress, we can see the reconstruction quality is still suboptimal, which means that you can have the holes or the reconstructed point cloud is still noisy. If you want to use this in computer graphics agents, you need to have a very high quality model as shown on the right. You can clearly see that there is a gap between the reconstructed models from the traditional method and what we want to have for 3D modeling in computer graphics applications. And I think the reconstruction quality of algorithms improved because there is a new form, because of a new form of the solution to the reconstruction problem. So previously, for traditional method, you need to detect the key point and match correspondences, and then you use the triangulation to get the 3D point. But this new form of solution is that now you can use the graphics rendering method here and make it differentiable. In this way, like by comparing the image difference between your ground truth captured images and the synthesized images from your reconstruction method, and then the gradient would be backpropagated to this 3D representation. So now you have your 3D reconstruction. There are a lot of great works in this field. Like this method, they use the different representation and use the different differentiable methods to get like very high quality result. Here we show like use the voxel grid, some method use a voxel grid or implicit fields. I think a popular method here is a Nerf. Everyone knows Nerf. So Nerf from like the images of a scene, and they learned a scene representation we presented as a radiance field, and they can render very high quality result from arbitrary views. However, if you want to extract surface from this learned scene representation, you can see like the result, it's good, but it has a lot of noise in this result. Why this is the case? Because the Nerf used the volume density as a scene representation, and this volume density lacks some surface constraints. So in Nerf, they think like the 3D scene can be represented as a volume representation. So they use the volume rendering to learn this representation. Okay, now we want to have the surface representation, for example, the SDF. So can we learn like surface representation? Actually, previous work proposed a method like to use the surface rendering to learn like this surface representation. So as shown here, this green curve, you can think about the ground truth curve. Ground truth surface. And here we simplified in this 2D domain, it's like a 2D curve. And this white line here is represent the predicted surface. However, if you look at the result of this method using surface rendering for surface representation learning, you found that this method easily gets stuck in a local minimum. And also it requires the additional mask as input to enforce this training conversion to the real surface. And why this is the case is because the surface rendering is not suitable or it's not efficient enough for learning scene representation. As I show here, this is because for the surface rendering, they assume like the ray color lines at this intersection point of the predicted surface and this camera ray. So during the backpropagation, the gradient would backpropagate to this intersection point only. If you think of Nerf is very efficient. This volume rendering is very efficient to learn scene representation. This is because for a camera ray, they would sample multiple points, and the gradient would backpropagate to all these sampled points. So we proposed a new method called Neus. We used the sign distance field, SDF, as a scene representation, and we used the volume rendering to learn this representation. I would not go into details, but the main challenge here is that we found if you directly using volume rendering to learn this surface, you have some bias issue. The surface would be, because in the volume rendering, you will accumulate colors before you hit the real surface. So like your predicted surface always a little bit biased to the location in front of the intersection point. Okay, so in Neus, we designed a new weight function, which is unbiased, so we can learn the geometry more accurately. Here show a comparison with the Nerf and the previous surface representation learning methods. And we can see, like, compared to previous method, Neus is more robust, and compared to Nerf without, the Neus without, it's smooth and has less noise. And the Neus can also reconstruct very high quality scene structures, as shown here. This is a very difficult case for scene structure reconstruction because this is a hybrid scene. Not only has consists of scene structures, but also have like this general object. So like the classical scene structure reconstruction method would not work in such kind of thing, but the Neus works quite well. And here we show more without of Neus. You can see it can handle a very complex geometry and also the appearance. And the last year, we launched the second version of Neus. Inspired by Instant NGP, we used the hash encoding for the Neus training. And we achieved like this fast training of Neus, so we can reconstruct such a thing within 2 minutes rather than like need hours to optimize this scene representation. And by modifying like this rendering algorithm, so previously in Nerf or Neus, we just used the volume rendering, but actually you can use the more physics-based rendering method, like in computer graphics. So you can have like handle like more complex illumination or this reflective object reconstruction. And we have also proposed a series of methods to learning a representation of animatable humans. So here, after we learned this animatable humans, we can drive like this avatars with arbitrary skeletal motions and render from novel views. So the core idea of the series of this method is that you have the input videos of a human, and then you first check its motion, and after that you estimate the texture and the geometry model of this human in time. And after that, you use the differentiable render to render this out, and then you calculate the image losses, and the gradient would backpropagate to the human geometry and appearance models, and then you can get very good results. This method, especially for like the humans, it requires a lot of views, like very dense views, especially for human performance capture. We ask like the performer to standing in this studio with like in a studio with a multi-view camera system, and this camera system needs to be synchronized and calibrated. I think. Some of you may already use this system. You know, like how much effort we should like capture the data in this system and process the data. So the problem here is that all this method I have just mentioned, that they are scene-specific reconstruction algorithm. So they require very dense view input of the 3D scene. If you reduce the number of views, they will have an uncertainty issue. What does this mean? For example, here we only show like one image. This is a single view image of this toy bear. And you want to predict what does the 3D look like, what does the novel views look like. So how to do that? So in this case, we need to learn priors from a large amount of data. Because, for example, you know like a single view images of a car and a chair, and then you know like all this how the 3D looks like and what is the normal views of this car from maybe the backside unseen visions. Which cannot be seen in this input image. And you can use this information and prior and use this for the initial case, which is this toy bear. So you can estimate what the 3D would be and what the novel views should like. Okay, so they have a lot of method. We call it the reconstruction-based method. Because they don't consider any uncertainty handling, which means that they just extract the information from the input view and then learn the mapping to the novel views. But if you can see here, without handling this uncertainty issue, if you look from the input view, it looks okay. But if you go back to the back view of this car, it's quite blurry. And also recently, there is a large model that trained on, because the people say, oh, maybe scaling would work if you just make this reconstruction method train a lot of data. Indeed, it's improved the quality, but if you see the back side view of this thing, it's still quite blurry. So so this uncertainty problem is that they have many possibilities for occluded vision, like different appearance, different geometry. And here in this talk, we focused on using diffusion models to model this uncertainty. They have two kinds of method, like for this generalized 3D reconstruction to handle this uncertainty issue. One is a direct 3D generation via a 3D diffusion models. The other kind is leveraging 2D diffusion models for 3D generation. If you are interested in this topic, and you can also check our recent survey about this topic. And first, we will talk about how to design like this 3D diffusion models to directly to handle like this uncertainty issue. So we proposed control 3D. It's presented today at 3DV. And here we not only care about a single image reconstruction, but we tackle like a more general problem, which means that you can give any conditional input, and then they can generate like a 3D for you. So here, like this control input can be not only like a single view image, but also can be like this edge map, segmentation map, or rendered of a mesh, or low resolution image, or even text. So previously, for this 3D diffusion model, they have two-stage training. So if you think about like how we train like a 2D diffusion model, we have like the ground truth image. We will add noise and denoise in on these ground truth images. So what the key challenge in designing 3D diffusion model is that how could we get this ground truth 3D representation? So here we give an example like this triplane as our 3D representation. Because we don't know, because we don't have like this 3D ground truth, this 3D ground truth representation, we cannot design like 3D diffusion models on top. And then here, like most of the method, like what they are doing is that they use the multi-view images of an object in the data set and run Nerf, and then they get like all these triplane representations. They use this at the synthetic, which is a synthetic data, but it's a ground truth 3D representation. After they get this ground truth 3D representation from the first stage, they would add noise and denoise in the second stage, which is very similar what we are doing in 2D diffusion model. So the problem here is that for the first stage, you need a dense multi-view data for training. How to solve this problem? So in this work, the control 3D, we want to train like a 3D diffusion model on single view image data set. And previously, we had some experience that like we can successfully train a 3D GAN on a single view image data set. And so here, like we first train a 3D GAN, which is a EG3D, on single view images. And then we have this ground truth triplane representation. And after that, we design like this 3D diffusion models based on this triplane representation. Okay, after we trained like this model, at inference time, we can make use of the advantages of a 2D diffusion model, which means that it's good for controllable synthesis. So for this here is similar to 2D diffusion model. This 3D diffusion model enables the controllable generation by two ways. So first is that you can train additional additional like encoder to map from conditioning to the latent features and do the cross attention with your denoiser network. And the second method is that you can define like a loss function here. So here, for example, if it's a single image, you can use your control input image and the rendered image from this triplane and calculate the color loss and use this as a guidance to guide your diffusion step. Okay, so here now you may ask, so why we need to learn diffusion models on top of 3D GANs? Because we can directly use the 3D GAN and like to control it and then generate this 3D model. This is because properties of these two models, like this 3D GAN and the diffusion model. For 3D GANs, actually they explore the whole 3D space, but they're not modeling the probability. And in contrast, diffusion model, they learn this score function in 3D. So they explicitly modeling like this probability. So this enables the better control. So what we are doing here is that we first learn a 3D GAN to explore the whole 3D space. But there is no explicit modeling of probability. And then we learn like diffusion models on the data synthesized by 3D GAN. So we learn this score function for us to do better controllable synthesis. So here we give like evidence why like this strategy is better. So in the middle for this pixel to pixel 3D, it's a controllable 3D GAN model. So if you see here, like for if you input this segmentation map, this would tend to generate some plan phase. But if you check out without, it can generate like more higher quality without. Also, here is another example, because if you train a 3D GAN, you can like, how to do control. Normally, like we either optimize the code in the W space or the code in the W plus space, or we train an additional network to predict the code in W space. Or here, because we have a triplane, we can optimize this triplane representation as well. But you can see here, like if you use the 3D GAN, because they don't have this explicit probability modeling, so this without is not very good. And if you have like a diffusion model on top of this 3D GAN, you can synthesize a very good result. Okay, here we show another applications of this method. For example, we can give the edge map, this edge map as an input, as a control input, and then we generate like this 3D model. Also, we can use the text as input, like to guide this diffusion model to generate a very reasonable like a 3D results. Okay, next, I will present another work. It's called single-stage diffusion nerf. So previously, we talked about like this 3D diffusion model. We have a two-stage training. The problem of a two-stage training is that you have like some issues on your in your reconstructed like this latent space. For example, here, this triplan, even that you use the 50 views for the nerf and to get this 3D representation, you can still see like without TV loss, it's quite noisy. And with the TV loss, it becomes better, but it loses some details. If you like reduced like your training set to the number of views in the training set to be 3 views, this problem becomes serial. Here you can see like with the only 3 views for to reconstruct this nerve, it's very bad. Even you have a very strong regularizer here, the result is not good. So in this paper, we proposed a single-stage joint training of this diffusion model and our this nerve model. And I will not go into details. So here what we are doing is that we combine this 2 parts and we jointly optimize these 2 parts with this loss function. One is the rendering loss, one is the diffusion loss. And after that, you can have like a better learned latent space with SSD nerve. So what's the advantage of this method? First, training is end-to-end. So you don't need like a 2-stage training. And also, this latent are regularized by this 3D diffusion prior. So we don't need additional design, like hand-designed losses as a regularizer. This diffusion priors can be used as a regularizer for the nerve reconstruction. And also, it enables a sparser view training. So you don't need like 50 views. You can use only 3 views for training. Here is some result of SSD nerve. On the left, it's an unconditional generation. On the right is that you can give like a single image as a guidance to guide your diffusion step, so they can do single view reconstruction. Okay, next we will move to the second kind of method for generalized 3D reconstruction. So it's to leverage 2D diffusion models to generate the new contents in the unseen regions. First, it's this Nerf-diff work. Okay, first we need to recap like what's the problem of reconstruction-based methods without this uncertainty modeling. We say like it's quite blurry in the unseen regions. And this, there is another line of work. They don't rely they don't need any 3D proxy. They just predict the novel views for a given input image. So here we show some result, although it looks good, but not fully multi-view consistent. So how could we use how to use the 2D diffusion model for 3D generation? For example, here we have 2D diffusion models, and then we generate, for example, one view, and we used the method SDS proposed by Dream Fusion or VSD proposed by Prolific Dreamer. And then we can have like a 3D representation. This 3D representation can be Nerf, triplane, or other Gaussian-based representations. Okay, in Nerf-diff, we have two parts. The first part is the image conditioner Nerf. Here it's similar to like a pixel Nerf, or this reconstruction-based method. We have an input view, and then we extract its local, like a pixel-wise features, and then we project it to 3D and render from the other view. And we're talking about this synthesized novel view. It's a 3D consistent, but very blurry, especially in the occluded region. And the second part is the conditional diffusion models. So you give like this pixel nerves the output at the conditioning to concat with the noise map and use the diffusion model, 2D diffusion model, to generate the output. And this output is sharp, but not 3D consistent. So here we show the result of the output of this conditional diffusion model. We call this model CDM. So why this is the case? Because although like in this pipeline, we used the pixel nerf as a conditioning, which means that we give this diffusion model some information about this view in 3D. But actually, this cannot ensure, like in the diffusion process, that for different views that they would have a different path. So they may not go into the same solution of like a multi-view consistent images of the object. So that is why you still get this 3D inconsistent result. To solve this problem, we proposed a Nerf-guided distillation method. This is a fine-tuning stage. So after we train this model, like train this image conditioned Nerf and this CDM model, and what we were doing is that we will alternate like these two steps we will first, for example, we will first like synthesize the novel views with the CDM conditioned on this Nerf output. And then we will use this output of the CDM to optimize our 3D representation. In this way, we use the very sharp images to try to reconstruct like our 3D model, to infer our 3D model to have a high, to find details. And then we used this 3D model's output, which is this pixel nerf output, to guide our the denoising step to be multi-view consistent. So we alternated these two steps. After that, we can get like both the 3D consistent and very sharp results. Here we show like a comparison. Previously, you already seen like this result from the reconstruction-based method. So here, we show like 3 results of our method. It's with our uploaded setting. So first is the output of the part 1. It's this image conditioned nerve. You can see like it's blurry in the occluded region. For the second result, it's the output of the second part. It's this CDM part. It's not consistent. So after this nerve-guided distillation, we can get, this is our full model, we can get 3D consistent and very sharp result. The same for this chair in the ShapeNet. You can see like it can also reconstruct the scene structures quite well. We also evaluated this method on the real images. Here is a Core 3D dataset. We can see like it also can generate pretty good result. So here the camera's a little bit flickering because this is used like the Core 3D datasets the camera poses. And after that, the reconfusion used like very similar ideas and extends it to scene level reconstruction and got this amazing result. Okay, recently there is the explosion of 3D generation models using pre-trained like 2D diffusion models. They distill like pre-trained 2D diffusion models, for example, 0, 1, 2, 3, or stable diffusion into 3D for this text to 3D or image to 3D generation task. But the problem of this method is, first is this Janus problem, is a multi-phase problem. This is very obvious in the vanilla 2D diffusion models. And you can see here in this animation. Also, like in the Nerf-diff, we need like the test time optimization. So it's very time consuming. What's the main, why this caused this problem is because this vanilla 2D diffusion models are not 3D aware. So a solution would be to make these 2D diffusion models 3D aware. The key problem here is that for vanilla 2D diffusion models, actually you only have like one probability distribution, and you have independent sampling. And this makes that like you generated the images from like different views that are not consistent. And here, maybe we can use like a joint probability distribution, which means that we can sample joint probability distribution and then to enforce like the multi-view consistency. So more specifically here, instead of using like a single view 2D diffusion model, you can use the multi-view diffusion models. And then you generate multi-view images, and you can use the like reconstruction method to get the geometry and appearance model. And this year we proposed two methods to like the high-level idea is the same. One is the Sync Dreamer, one is the Wonder 3D. Next, I will use the Wonder 3D as an example to tell you like how to design like this multi-view diffusion models. Actually, this method is very simple but very efficient. So what we do here is that we use the like 0, 1, 2, 3 model, and then we find like modify like this model, and then we given like an input image, we will output not only like one image, but we output like a multi-view images, and also it's a normal maps. So here, like during the diffusion stage, we will use the like we proposed this multi-view self-attention, which will make this model to aware of like this sampling stage in other views. So you kind of communicate between like different views when doing diffusion. And also, we proposed like the cost domain self-attention. These two domains is the normal and the color. And because we know like the normal would help like the color recovery, and also this color information would also help like to get a better normal. So with these two like attention mechanisms, we can get a very high quality texture, high quality output, multi-view output. And this is a multi-view output because they have some, you do like a joint sampling for all these multi-views, so it would be more consistent, more multi-view consistent. And after that, because here we have a normal, so we can use some fusion method to get a good like geometry and the text model. And here we show some result of a Wonder 3D. So on the left, it's the input images. And actually, we found like this model it's very efficient in terms of that. Like they don't need a lot of training data. They don't need a lot of training data, and the generalization is very good. So here we test this on the in the wild images, which is downloaded from website, from online, and then we can use these images and to estimate like the normal maps and the multi-view images, and then we run like the diffusion method to get the final geometry and the textures. We also evaluated this method on another data set, which haven't seen during training. It's this animal data set. So given this, also the left are input images. And also you have like the normal maps and the images synthesized by the model, synthesized by Wonder 3D model. And then you have like the final output. Since you have like this 3D geometry, and you can also use the 3D printer to print it out. It's super cool. In summary, today we talk about scene-specific 3D reconstruction. And then the main problem here is that you need very dense input views. And then we need like a method which we call it a generalized 3D reconstruction method to handle this uncertainty problem if you only give like a single input image. And for this scene-specific 3D reconstruction, we introduced like the method for static scenes, which is Neus, Neus 2, and Neural. And we also talked about like this dynamic scene reconstruction, HD humans, the new actor, and the DDC, and they all need a very dense input and a very heavy setup, especially for animatable human modeling. And then we move to generalize the 3D reconstruction method, and we talk about two kinds of method. One is the 3D diffusion method, which just design like is just design like a 3D diffusion models, and we talk about how we can get like the ground truth, the 3D representation for the diffusion process. And also you can use the like 2D diffusion, and then distill this. For example, distilling like this single view diffusion model into a 3D model. And we talk about like a Nerf-diff. And then we talk about like this multi-view diffusion models, which is the Think-Dreamer, Wonder 3D. We use the Wonder 3D as an example. And also here I should mention another advantage of Wonder 3D is that we don't need any very time-consuming test time optimization process. We can only have like a forward pass. The only problem is that diffusion model currently need a lot of steps for denoising, so it's quite slow. So what's next? First, it's towards real-time single-view 3D reconstruction, because it's very important in 3D reconstruction, especially if you want to use these algorithms for some real-time applications in robotics. And we talk about currently one problem is that like diffusion models, it's a diffusion model needs like a very time-consuming denoising steps. So here, these are consistency models, like this is a single-step 2D diffusion models. We also proposed one model called Boot. It's which is like a single-step 2D diffusion model. And how could we use like this kind of technologies for the 3D diffusion model design? This is still like a question. Other important problems are like large-scale scene reconstruction and dynamic scene reconstruction. For example, how could we reconstruct like this dynamic scenes from a monocular video? It is still very, very challenging. We live in a very complex world. That is why we need to handle a lot of cases. So here you can see like in this video, there are a lot of occlusions and also a lot of motions. How could we reconstruct such complex things? The current method still cannot achieve that. At the end, I want to thank all my co-authors. Without them, I could not present this work, like this amazing work here today. And thank you very much for your attention.
Thanks a lot, Lingjie. We have now some time for questions. If you want to ask questions, there's microphone stands, or you can also raise your hand. I thought I saw a hand, but then, okay.
So on the Wonder 3D side, like the surfaces look like super smooth, but you know, from the days of Nerf, you know that view-dependent effects can corrupt the surface geometry and give you like weird cavities and so on. So what tricks are you doing to control it?
You talk about the Wonder 3D paper that the surface is not very detailed. Yeah, I think one problem here. So I think it's still like, for example, this normal map, currently it's still lack of some details. We also, like this model currently is trained on a small scale of a data set. Not we didn't use like the full observers data set. We just select a part. I think this may affect some quality. But if I didn't show like a comparison here with the other method. Actually, if you train like other method on the same scale of a training set, the result is still not quite good. So I think here maybe scaling can work to have like a higher quality results.
I have one question regarding also the future work that you explained. You were talking about now a need to make these diffusion-based approaches as real-time as possible. And so in that case, you clearly need to sacrifice, let's say, typically now, for example, the quality that you could get out of the, let's say, 3D shape that you can generate. How much do you think let's say, getting it down to a real-time performance is important? Do you have some applications in mind that would have this type of strict requirement? And is there any trade-off that we can look there?
I think there are a wide range of applications, especially in robotics. For example, if you want to like do some interaction, for example, for the video I showed at the beginning, if you want to help the patient to do like help them to do a task, you definitely need like a very real-time reconstruction of like, for example, how this person is move, how they touch with the like the chairs, how they like the surface is deformed, so you can make the robot know like how to do the action. So I think this is like a real-time application. There are a lot. And in terms of quality, yeah, for like in boot, we see like there is a like a quality drops when you kind of reduce the number of sampling or denoising steps. So that is why there is still room to improve like the quality. But I think this is a very important problem. We are still looking into this problem. Yeah.
We seem not to have any other question. We're also close to our time, so we would like to thank again our invited speaker, Professor Liu, for being with us today. Thank you.
Thank you.
This is also the end of our second day of 3DV, so thanks for being with us and see you tomorrow for our third and last day. Thank you.